Hola. Bueno, primero agradeceros a todos vuestra asistencia.
Good afternoon. I'd like to thank you all for attending this roundtable. We're going to open a roundtable dealing with machinery, failure and security and turbines for energy generation. I'm going to be very, very brief in introducing the panelists because we really want to focus on their presentations. I'm going to briefly introduce you to the four speakers or panelists. We have excellent representatives of the main stakeholders that play an important role in power generation. We have a representative from engineering, from operations of plants. We have a technology representative. And I hope you find this roundtable interesting and insightful, and I hope it encourages members of the audience to ask questions and make comments. I'm sure that we'll all enjoy and learn very much from this roundtable. To my left, I have Francisco Javier Lacalle. He is here in representation of Tecnatom. He holds a degree in industrial chemistry, and he has worked for more than 23 years in the world of generation, more specifically the engineering thereof. He has worked in different kinds of plants, thermal, nuclear plants, and during the past 4 years, he has been working in Tecnatom. He is in charge of energy and industry of Tecnatom, and he will be the first speaker. Secondly, we will have the pleasure and the honor to listen Santiago Garcia. He holds a degree in chemical science as well, holds a master in business administration. He has worn many different hats. He's a trainer, a writer. He has worked in ops and maintenance in power plants. He was in charge of the first combined cycle plant that was built here in Spain. I'm sure we're going to enjoy his presentation very much as well. Thirdly, we will listen to Daniel Elias, who is here on behalf of Iberdrola. And Daniel, let me check my notes on my mobile phone. I'm afraid I didn't have time to study your CV as I should. He is in charge of maintenance for the northern region of thermal generation in Iberdrola. He has broad experience in maintenance and operation of thermal plants. And he has been the maintenance manager and the ops manager in several plants since the year 2000. Santurce, Pasajes. He also worked in Longinet in Scotland. And he is currently in charge of maintenance for combined cycle in the northern region of Spain. Thanks very much for joining us as well. And last but not least, we're going to listen from the point of view of the providers, the vendors, the technology experts. Our last speaker is here in representation of Siemens. He works in the division that develops large-scale turbines. His name is Falk Aserman, project manager for first-time application and product commercialization of gas turbine service products. He will deliver his presentation in English. He has worked in Siemens for many years. He has held different positions, and during the past year, he has focused on the new technologies for the development of new turbines. And I wanted to be brief in these introductions because I think that it's time for us to listen to the panelists. And I think that their presentations are going to complete what Pedro Soria exposed earlier. Good morning, ladies and gentlemen. Thanks very much, Mafre, for inviting me to participate in this seminar. I don't want to bore you. I'll try to be short and sweet. My presentation is divided into 5 parts. I'll give you a brief introduction, and I'm going to refer to some of the technical conclusions that Pedro Soria referred to earlier during his opening presentation. Second, I'll talk about degradation phenomena in steam turbine. I'll share with you some examples of incidents in steam turbines. And I'll try to explain why gas turbines are exposed to a higher incident rate than steam turbines. And I'll try to compare the gas and the steam turbines to explain that. And last, I'll talk about degradation or wear phenomena in gas turbines. I know that Santiago Garcia will address more practical issues pertaining to the maintenance of turbines. I'm going to be a bit more general in my approach. Let me start with the background information. If we analyze the conclusions of the study presented by MAFRE, and we focus on two main issues, we see that there's a relatively high incident rate of turbines if compared to other generation equipment. In the case of gas turbines, the accident or incident rate is higher than that of steam turbines, and this is perfectly logical. Gas turbines operate at more demanding conditions as opposed to steam turbines. During the 90s, there was a vertiginous race to increase the yield and the performance of gas turbines. And we have technology experts and vendors in the room. And if I may say, perhaps at that time, some turbines were sold and commercialized with insufficient operation hours. We had the challenge of reaching 60% yield in combined cycle, and the conditions in which the turbines operated were extremely demanding. The elements that have suffered most and that have caused a greater number of incidents are the blades. Later on, I'll explain to you the different degradation phenomena that affect the blades in gas turbines. In the case of steam turbines, the incident rate is lower, and this is due to errors in or failures in control and regulation elements. This is also quite understandable. The gas turbines have suffered problems as a result of degradation of blades, as a result of the very extreme circumstances and the number of startups and shutdowns that they need to face. In the Spanish in the territory, we have 102,000 megawatts of installed capacity, and the power peak in 2014 was 40,000 megawatts. This means that the time of the day with greatest consumption involved an output of 40,000 megawatts out of the 102,000 megawatts of installed capacity. As you can imagine, this means that due to a series of technical restraints of our grid, we have some combined cycle plants that are starting up and shutting down virtually every day. As for the main failures in steam turbines, most of these failures have to do with the control and regulation elements. This is very logical as well. It's true that the system is much less rigid than in gas turbines. It's more difficult to make an operations mistake in the gas turbines that are started up with sequencers. There are many backups and redundancies and safeguard mechanisms that are in place. So it's hard to make a human error in the case of gas turbines. In the case of steam turbines, the supervision during startup is done not by an automated system but by operations staff. Regarding technology, we often say that the conventional thermal power plant performance is relatively good. We have an average performance of those plants that use gas turbines. In the case of biomass plants and solar thermal plants, the level of performance is worse. I think this is due to several aspects or several reasons. First of which cannot be influenced on conventional thermal power plants. When they start up, they operate in a more stable manner. They are exposed to less load variations, to a lower number of startup and shutdowns. In the case of gas and thermal solar plants, the number of startups and shutdowns is much greater. However, there's a second factor element that leads to greater incident rate in the plants. And I think that engineering companies can influence on this second factor, as well as the training companies. From our point of view, the operations staff of conventional thermal power plants who have accumulated long hours of operation, and they are perhaps more highly qualified than the operations staff in other more recent plants. And now let me refer to those systems that exist to subsidize or to assist operation. In Spain, we see that most of the plants have control systems based on a limited number of alarms. And this allows us to supervise and monitor operation pretty easily. If we go to a coal plant, we have perhaps a few hundreds of alarms in place. However, much to the contrary, in some combined cycle plants, we have 15,000 alarm signals. 15,000 alarm signals. And probably we have 10, 20 alarms that pop up every minute or every 2 minutes. So this means that we have an operator that doesn't have enough time to analyze what is happening in the plant, that has to deal with a huge number of alarms. It's very hard to manage. Some years ago, when the coal plants were installed, placing alarms was expensive. You had to lay cable, have some space reserved on the screen. But now what is expensive is to remove the alarms. The vendors of the equipment believe that all the signs can have the category or the status of alarms. Sometimes for service air instruments, we have 125 alarm signs. And this means that we need to devote many man-hours to handle that. So this means that what is expensive is to have a limited number of alarms, which is a situation contrary to what happened in the past. I'd also like to insist on the operations manual. The combined cycle plants, perhaps to a lesser extent, but the biomass and solar thermal plants, often lack an operations manual, at least many of them. So this translates into the fact that the plants aren't appropriately managed, are not managed to the best standards. Sometimes operations depends on the criterion of the shift manager that is in charge at the time. So there is less rigor. Well, after this brief introduction, I'm going to refer to the degradation phenomena in steam turbines, then in gas turbines, and I'll show you some examples of wear and degradations in both gas and steam turbines. I'm going to devote very little time to this section. My colleagues will focus on this with greater detail, so I'm just going to run through it. The main causes of degradation in gas turbines are fatigue phenomena, both in low cycle and in high cycle, i.e. thermal origin tensions produced during startup. Then we also have the high cycle fatigue, stress corrosion cracking. We also have identified erosion corrosion phenomenon, the weakening of material or fretting. If we take a look at really understanding, if we try to understand each of these phenomena, we see that in the case of low cycle fatigue, this low cycle fatigue can be defined as the gradual damage or degradation of a material produced as a result of the subsequent heating and cooling cycles that translate into expansion and contraction of a material. There is a plastic deformation, and this thermal fatigue occurs mostly during startups, outages, shutdowns, and load variations. In the case of the heat turbines, not all the plants have the mechanisms in place to control the cooling rate when the plant is shut down. Sometimes the managers are in a hurry to restart the plants, and this leads to fatigue. In the case of high cycle fatigue, most of these cases are caused by vibrations. Here we have identified the critical areas that are most exposed or vulnerable to fatigue: the high pressure rotor. And we're basically referring to the bore of the turbine, and the low pressure rotor. We have a low cycle fatigue with resonance in startups and shutdowns. Then we have the mobile blades. We also find that bearings and the rotor are also very vulnerable to fatigue. I'm sure in my presentation will be uploaded on the website, so you can take a look at the details later on. I'm going to run through it now. We take a look at the third degradation phenomena. It's SCC, or stress corrosion cracking, that occurs when there's a combined action of a corrosive agent, polluted moist steam, and a mechanical effort. And at this point, I'd like to clarify something which isn't specified here in my presentation, which is the fact that often stress corrosion cracking is caused as a result of the steam becoming polluted, as a result of the fact that in many power plants the control systems aren't well adjusted. The steam temperatures aren't well adjusted.
This prevents the steam to go higher than 50-30, for which the turbines are designed. Sometimes the steam raises higher in temperature, and quite often we have plants where for hours they've got to work with these tempering devices opened. You usually inject pulverized or sprayed water in the main steam lines, and this sprayed water might have more or less solid particles than the steam itself in the steam turbine. And this, from a running point of view, we might prevent the unnecessary use of these temperature controller devices. So usually when there are these changes, we usually might see small cracks, and the efforts related to this operation, the creation of these cracks might be not very severe. It might be related to the state of the turbine, and we usually find many data, because in the States we see that after some surveys, whenever there have been some failures due to corrosion under tension, this has led to disaster. Sometimes even it's led to fatalities, to the loss of human lives. Okay, I'm going to skip these CCs because we're going to see this in another presentation. And then we've got other degrading phenomenon like erosion for corrosion. This might be related to the absorption of hydrogen. Then we've got fretting of wearing out. And then we've got some of the specific parameters of this degradation, like the average of temperatures, the drop of pressure and the performance. We might see some vibrations, and we might also see problems with the lubricants. These are the periodical inspections that of the turbines, and then the N and Ds that we've got to implement, and then also the magnetic particles, the X-rays, and so on and so forth. And then also we see here how we can analyze the whole of the turbine to see what the remaining life is and the inspecting period advised is. And then we've got the main mechanism of mitigation, which is common sense, to optimize the number of shutdowns and startups, then to do a preheating of the turbine, to study the critical speeds, to avoid situations in the condenser, and to reduce as much as possible the vibration. Then we have some examples of some turbine incidents. Here there was a failure in this steam turbine because it was not coupled, and when they were going to undertake the overspeed test, well, it didn't work properly. There you see the low pressure elements, how they're before and after. There was a fire in the high pressure element. There you can appreciate what the shaft coupling looked like after that incident. Then we have another example here. The turbine ran out of lubricant oil, and there you see there was on the first picture that you see how that element got broken because the bearing was fretting against that element that got broken finally. And then you see what the shell looked like. Then the coupling of the turbine with the generator. Then there was a fire, and you can even appreciate the hole in the roof of the premises. And it seems that part of the turbine had to was propelled through the roof. Well, they were using steam, a very good steam, demineralized as work fluid with the right pH and the right level of oxygen. And We used also atmospheric air, and we've been adding to it some fuel. Then this fuel and this air might have some salt, some sediment, sodium, vanadium, and then also there is a power control done to see whether the inlet temperature at the turbine is proper. So sometimes it suffers from some thermal tension, and then we work with temperatures that go up to 1,200, and this leads to having sophisticated cooling systems. And then finally, yes, a short review of the degrading phenomena that happen in the gas turbines, like creep burning, hot corrosion, fatigue erosion, and impact. And then since I'm running out of time, I'm just going to show to you some of the results in these pictures of these phenomena like creep. Here we have this case of creeping. The gases from the turbine, they expand, they're not homogenized, and there's a very high profile of temperature. There you see how they were too hot in one area. Here we see an example of burning. And then, when we talk about corrosion, simply I want to mention that it is especially critical in the in islands, because they use gasoline, and it might have sulfur, vanadium, potassium, so it might be polluted. Then we've got here two charts in which we appreciate how, if we increase the PPTs of potassium and vanadium, it changes, and then the life expectancy of the blades might reduce up to a 10%. Then same goes for the chamber. Then when we see these cases of fatigue or wearing, we see how the blades lose their original shape, and also how they might get damaged due to this fatigue. Then erosion due to some acids, and we see how the outside layer was fully destroyed, and then some problems of impactions. So I guess I've been able, or I hope I've been able to share with you the content of my presentation, and should you have any further doubts or comments, I'll be eager to answer them during the Q&A. And also for the audience to know that the whole of the presentation can be downloaded from the website. So without any further ado, I'm going to give the floor to Santiago Garcia. He's the technical manager of Renovatec. He's going to talk about maintenance.
Bueno, buenos días a todos.
Well, good morning, ladies and gentlemen. First of all, congratulations, Pedro, on your presentation. I mean, I don't know what else I could add, because some of the conclusions were something that we were not really expected, even though I work in this field, and I should have kind of very good information, but it does not match your information. So I guess you're working with a larger sample, and that leads to some conclusions which are not the conclusions I was expecting. I am impressed by how these valves, regulation valves, are responsible for such a large part of these incidents, and also how it seems that, according to the comments in the insurance field, it is very well known that after intervention, the possibility of having an incident is still very high. The all mechanicians used to say, well, if something works, do not touch it. And it seems this is the same conclusion as Pedro's. So I hope we will later on be able to dwell on it. Well, my name is Santiago Garcia. I am the technical manager of Renovotech. We basically work in the field of energy, and we also do industrial maintenance. One of my activities is the survey of incidents or failure that will have an impact on lawyers or insurance companies or on the premises owners. We also do training and other activities. I am an expert on turbines. I'm not just a small expert. No, I am the expert on turbines. And I've got to say it because I went wrong so often that I can now say that if anything could go wrong, I've seen it and I've done it. So this is why I'm an expert with a capital E nowadays. So, I mean, this is fruit of practice. I bet you. I mean, I can really tell you. Unfortunately, I am an expert through experience. And since I only have 20 minutes to talk to you, I've got to focus on something, and I wanted to sort of provide you some sort of practical message. I don't want to talk about sort of theoretical things because you know about them. So I wanted to focus on some aspects to sort of give you an inside view. And whenever we talk about turbines, design is very important, as our colleague from Technoturn said. Many turbines have been implemented without really very sophisticated design. Sometimes also some of the operators, especially now with the new emerging technologies or new technologies, there are many operators that did not know this field. They came from another field and they've been hired simply because they're very close to the premises, not because they are very good as technicians. And this is how we usually call them sort of the neighbors that give up on their favorite hobby and decide to do this. So, I mean, we've got to sort of brief them on some of the concepts which are of paramount importance for this kind of operations. We're not going to sort of get into every detail about how the fact of not running properly the premises might be the cause of some of the incidents. I'm going to talk about the maintenance policies because they are, on a large part, responsible of most of the incidents in a turbine. Okay, let's talk about the current scenario. The current scenario is that we have, as Francisco said, a power which is smaller in the plants. Many powers only run for some few hours, and the pool prices are low. So we have like an overcapacity. So we used to have 180,000 megawatts installed, and since they're no longer that profitable, we've got to make them run for a shorter time. And we, given this scenario, we try to cut down on cost, and one of the costs is precisely maintenance. And you can reduce the cost of running your premise, but the thing is there are some maintenance expenses that could be reduced, because reducing that is just reducing not very important things. It's like removing the fat out of your body, not touching your muscles. But, I mean, at a certain point, you are removing fat, but if you keep on cutting down on cost, you end up touching your muscles or the muscles of these installations as well. And there's been such a cut in the maintenance budget that this is leading to failures, to lack of availability of people and equipment. And this leads to the fact that maybe in the coming years we're going to see an increase in the incident rate related to this cut in maintenance. So cutting down the maintenance budget has got mainly three repercussions. So that is liability, availability, and the maintenance cost might go down as well. And also the life cycle also might become shorter. So it will be running for fewer hours, so it will not be available that often. The cost of maintenance, even though initially we might consider cutting it down, we will end up with an increase of the maintenance because the life cycle or the lifespan of a plant is going to become shorter. So this happens if we cut maintenance budget without doing it properly. So we can face this situation without affecting or having a negative impact on availability, liability, cost of maintenance, lifespan of the premises, and without running the risk of having a failure. We can do it. The answer to this question, can we do this? Yes, is yes, but we've got to do it properly. We are working more than 50 powers all over Spain, and we're there somehow, some as advisors, some we develop the maintenance plan or scheme. Sometimes we intervene whenever there's an incident. Sometimes we do training for their staff. So we have quite a large population or sample to know where the cuts are happening. And we think that we can make cuts on maintenance, but you've got to do it properly. So we might go for cuts in staff, in the maintenance plan, in the outsourcing policy, in the spare parts policy, in the software tools that we use to manage maintenance, in non-operational managerial tools, and later on we'll let you know what this means exactly. And then we've got to also maybe do audits. That is, we do a benchmark with other premises. Well, talking about staff, what do we need nowadays? And this slide is thought for Europe. It does not concern so much South America or Africa, which are the markets that we know, because we do not know much about the Asian market. But this slide concerns rather Europe, where there is less of a demand of staff in the premises, but that means also that the people they need, they want them to be people with a higher qualification. And the people that should then be working in this power plant should be more polyvalent and know better how the installations work. Then we can also cut on maintenance, but that implies some changes, and I'm glad that this slide